in this problem, I envision it looks something like this. That I have the plank, and the plank's 10 meters long, right?
Yeah.
And I have these cinder blocks that are 6 meters apart. I know one of you complained that that wasn't centered, but is that okay for my drawing? So now we want this to be in static equilibrium, but we're told that a person is going to stand here at the very end. And let's see, we have more information about this, right? It's a 60 kilogram plank, and the person is 90 kilograms. And I think we also were told that the center of mass of the plank is at its center. So somewhere right about there. And that's 600 newtons. And the person is 900 newtons. We've got a normal force here. I'm going to put this as the right normal force and the left normal force. That all good? I kind of think that the left normal force might be downwards and not upwards. Like maybe it has to hold on to the edge of the plank and not push up on the edge of the plank. But I don't know for sure. But that's what the question is asking. So I'm going to treat this like a standard statics question and say that the net force has to be equal to 0 and the net torque has to also be equal to 0. I'm going to put the pivot point on the right support, and I'm going to do the problem from there. Does that work out for all of you? Okay, so I'm going to do the easy stuff first. 600 plus 900 has to equal NL plus NR. That's just the net force portion of the problem, and I think that that's pretty straightforward. I don't need that unless I want to get both of them, but I thought I'd throw that down there anyways. Any question about that? If I choose the pivot point as I have, then I see that there's going to be three torques. There's going to be a torque from the 600 Newton object, the torque from the 900 Newton object, and the torque from the normal force on the left. Are those good for our three torques? RF sine of the angle. So starting with the 600 Newton plank, R is going to be 1. F is 600 sine 90 degrees. And that torque is going to be out of the board, so that's positive. Any question about that? All right. So I've also got the person. All very straightforward there. But their torque is going to be into the board, so that's negative. And lastly, I have the torque from the end. Based on the way I've drawn it, it's also a negative torque. So negative, it is 6 meters away. It is N, L. There's also sine 90 degrees. Those have to sum to give me 0. So getting rid of all the sine 90s, I'm going to have, combine them, 600 minus 3600 minus 6NL equals 0. And that looks like negative 6NL equals 3,000. So it looks like the left side has to provide a negative 500 Newton force in order to keep the system at equilibrium. That means that it's got to pull downwards with 500 newtons. to hold the person in place. Or else the plank just rotates, which is what's probably going to happen. You'd never make it out there if it was just resting on top. While we're doing it, let's say that the plank, let's say it does have something holding it down here. Then consider this for just a minute. That'd be 600 plus 900 equals negative 500 plus the normal force from the right cinder block. That's 1,500 on the left plus another 500. The right cinder block has to provide 2,000 newtons of upwards force to be a pivot point. That's a lot. It's more than the combined weight of the two things. That's because the ground's having to also pull downwards on the plank to hold it in place. Cinder block would probably crumble under this if it was actually cinder blocks. So I want to point out that you sometimes get results that might be unusual, but the cinder block provides more force than the weight of the system. A lot more force than the weight of the system. And when it comes to the kinds of questions on AP, asking about that seems like the direction AP might go. Okay. That's it for me. Is that pretty thorough? Yes, sir.
So why does it provide? So why is there more force? Is it because it's like the force and it's
Yeah. That person standing that far out gains an incredible amount of leverage over the system. So if we were to successfully mount this in place, like say we got something really, really, good and sturdy that would clamp on to the end of that board. Well, him pushing down that far away from the pivot point creates an enormous amount of pressure on that piece. And it's because he's gaining leverage. Same reason why if you get a large enough wrench, you'll be able to break that bolt. Same idea. You get a large enough reference, you're going to apply this kind of force. This is how a lot of things in your everyday life kind of work. Anybody ever used a nutcracker before? This is the whole process for a nutcracker. What does a nutcracker look like? But you hold on to the outside handle and the nut goes in the middle someplace. Right? That's what this is. So if this were a nutcracker, the nut would go right here and the hinge would be here. Does that make sense? You guys see what I'm talking about? Or even like crab crackers and stuff like that for lobster and all that. Similar ideas. You put the food kind of inside there and you push down on it. It's not much different from the way a pair of like pliers might work. Pliers use a similar leveraging system. The only difference is that you actually gain more leverage using like something to crack crab than something else. Here's a pair of pliers, right? You're going to have a point that fastens them together here. You're pulling these sides together, but you gain leverage by having a longer torque arm. You have to have equal torque on both sides, so by this side being shorter, the force that you get here has to be greater. These actually have names. Or class 1 lever, class 2 lever, class 3 lever. If you get into any kind of mechanics, you choose these kind of things based on how much force you get at the pivot points and stuff like that. This is the whole principle of like how scissors work, stuff like that. Anything that's like this is leveraging your ability to apply force. So, is that good? Does that answer your question pretty well? All right. So this is our ladder again. So do you remember those? And this is theta as designated in the problem. We're going to have to be a little more careful about that in this problem. You can. And that's likely what I'm going to do. There are some alternatives, because remember, we're trying to solve for something here. We had that before. This does make that trouble. So yeah, you're right. This would be 90 minus theta. Is that okay? But we'll see how that's going to play out here in a minute. I've got mg, and that also is happening at 90 minus theta. I've got capital Mg, and that's happening at 90 minus theta. And then I have normal force from the wall. And that's happening at theta. Any questions about those choices? All right, so we already know from prior experience here that net force in the x direction is going to equal 0. So the static frictional force is going to equal the normal force from the wall. And net force in the y also equals 0. So normal force from the ground minus mg minus big MG equals 0. So I think we've handled all the force portions of the problem. Is that good? I'm going to choose the pivot point, the fulcrum, to be right here. That seems to be a good place to go. All my measurements were already made relative to this point. This is at L/2. This is at D, and this is at L. Is that all good for you guys? All right, so let's sketch out our torques. So I have torque from the mg, torque from big MG, and torque from the normal force in the wall. Those are our 3 torques. From mg, now here's where we have to start being kind of careful. My torque arm length is L/2. Size of the force is mg. And the angle is going to be sine of 90 minus theta. That's also cosine of theta. And I'm going to encourage us to consider putting that in terms of theta, not 90 minus theta. Does everybody follow what I'm saying? So if you don't, then I need you to catch up with me and know that this is a trig identity that you should be able to use. If you want, we can prove it real fast so you know why that is true. Does anybody need me to prove this to you? Okay, so we feel confident that it's okay to use that? All right, then I'm going to go ahead and use it now. Our next thing is to figure out what direction that torque is. That torque is into the board, so that makes this negative. The next person is also going to be negative because that torque's in the same direction. Distance D, mg, and it is also cosine of theta. And lastly, the normal force will be positive. It happens at L. It's normal force in the wall, and it's sine of theta. All right, so press on. These have to sum to be 0 or else the ladder is sliding. So we get not a particularly easy expression, but we'll get L n wall sine theta equals mg L/2 cosine theta plus capital MG D over, not it's just cosine theta. There's nothing pretty about this, so we need an expression for the normal force from the wall. So I figure that's where we go next. That just means dividing by L and sine theta. And this is ugly. Very ugly. So there are some things we can do, but let's write it all out. So it's just nasty. Okay, so is everybody okay with that? Any questions about how I got here or what this looks like? All right, now, there's nothing ultimately I can do to make that look much better. I mean, I could write this a little simpler by distributing the L sine theta. That would give me mg over 2 cotangent theta. That's what happens when I take this and divide it into that. Nothing special about it. I'm just making it slightly less terrible looking. But that's going to make this mg d over L cotangent theta. Nothing pretty, but that's just it being narrowed down. So we need this because this also equals the friction from the ground, the static friction. Now we also have an expression for the normal force from the ground. That's from earlier. Bring that over there. Normal force from the ground is equal to mg plus mg. We're looking for an expression for the coefficient of static friction. So, static friction is less than or equal to mu s times the normal force. This is the normal force from the ground. So, mu s is greater than, less than, equal to, here we go, mg plus mg, and mg over 2 cotangent theta plus big mg d over L cotangent theta. It's icky. Just icky. It can be made to look a little nicer, but you're not going to get any miracles here. If I was, wondering how I might make it look nicer, I might factor out the cotangent and factor out the g. So there's a g in every term, so the g can just be factored out and put away, and I get, in parentheses, m over 2 plus md over L divided by m plus m, all times cotangent theta. Now, I agree, this is a mess. There's no doubt. But if you're the guy who makes the sticker on the ladder to tell you what angle to use, do you see that there is a relationship now between the angle and what the coefficient has to be? It's a pretty clear relationship. It's kind of telling you that there's probably a sweet spot for that angle. Right? We know cotangent has kind of a range to it, doesn't it? It has the same range as tangent. Can go to infinity in one direction and 0 in the other. That's a range, all right. There's clearly stuff about where you can stand here. This D over L ratio isn't accidental. This tells you that there's a safe range on where to stand and where there isn't. And that ratio shows up in there on purpose. The fact that the weight on the bottom is here, that should be obvious. Put more weight on the ladder, I get more friction. Good job. That makes me reduce how much friction I need. But this ratio here, this D over L, that plays a pretty big role in determining how much friction I'm going to need. You notice you get higher up there, you need more friction. As D gets bigger compared to L, you're going to need more of a coefficient of friction to stay there. I get that this is complicated, and you may not like stepping through this, but to me, this is how the science actually plays out. This is why they've picked some things, but also why it says all over it, every ladder you've ever bought, warning, don't be an idiot on the ladder. Because we've decided that there's just some ranges we think in which it will work. And nobody outside of a physics class has any idea what this is. So they're just hoping you're putting it on ground that's going to have some kind of coefficient. You understand that they've picked a value that they think most ground is. And they're sticking with it. If you've ever actually bought a ladder, mine has claws on the end in case it's, a situation in which I'm on snow or ice. Or I'm supposed to stick the claws in and not use the The axle just skids on the bottom. So, and I've never had my ladder slide out from under me, but I've definitely had it move around under me. You know, usually it's because I'm doing something stupid and trying to get a little bit higher than I should be. And I'm probably, bigger than I'm supposed to be too. And that's not helping matters at all. So there you go. I'll stop boring you. But I like this problem. I think it's fine. It's not pretty. There's no mess here. There's nothing. It doesn't come out to be something nice and clean, if that's what you're hoping for, where everything canceled out and the answer is 4. It's not. There's more to it than that. All right. That was number 4. So this is the answer to number 4. Next. I gave you a hint on number 6. Did anybody take me up on the hint? Did you draw it the way I suggested you draw it? Because the hint I gave is that 6 is a 3, 4, 5 triangle, which is a right triangle. So I was saying that you have to do a 2-dimensional analysis on this. You have to find the center of mass in the x direction and the center of mass in the y direction. So I recommended that you set the triangle up so that one of the pieces of wood was lined up in the x direction and one in the y direction. So let's try to see if I can do that. So this is going to be, let's make that one the 4-meter long one. That's the 3-meter long one. And so a 3, 4, 5 triangle. Any question about that? Well, it says one is a piece of 3 meters, one is 4 meters, and the other is 5 meters, are arranged in a triangle. The pieces each have the same linear density. Draw a picture and find the center. So I don't know whether you thought to do this or not, but if they all have the same linear density and they don't tell me what the linear density is, I'm just going to say that the linear density is 1 kilogram per meter. So this piece is 5 kilograms, 3 kilograms, and 4 kilograms. You could have said, put lambda in there and said 1 is 3 lambda, 1 is 4 lambda, and 1 is 5 lambda. But the lambda is going to cancel out. So if you'd like me to do it with the little lambdas in there, that's fine. But I'm going to do it this way because I think it's easier. Also, center of mass of each piece is at the center of the piece. So this is a point mass located at 1.5 meters from the x-axis. And this is a point mass located 2 meters. So you guys have to do the work for this next one. We need to figure out where this next one is. But we need where this piece is. We need its x-coordinate and its y-coordinate. Now, I'm just going to be plain with you. Can you do that, or do you need me to do that? This is not a choice. This is silence. It's one or the other. So I'm saying that because either none of you attempted this one and you did part B. You didn't think to do this, that's fine. Or you have the answer for where this coordinate is. So I asked whether you want me to do this or you've done this. So since it was silence, I'm going to just call on people until I find out what those coordinates are. Or would you like me to do this? Because I don't care. But I just want you to answer a question when asked. So I'll ask again and be polite. Do you need me to do this, or do you have the coordinate for me? You want me to do it? Okay. For me to do it, I'm going to need to find either this angle or this angle. One or the other. Doesn't make a difference which one, but I have all the information I need to find that angle. Now, I actually don't think I'm going to need the angle because it's a 3, 4, 5 triangle. So let's say I choose this angle for my work. and I make that theta. Sine of theta is 3/5. Cosine of theta is 4/5. And tangent of theta is 3/4. The AP exam uses the 3, 4, 5 triangle all the time because these ratios are there. So please internalize that. That's why you use a 3, 4, 5. And that's why they're in a lot of the work. I'm trying to find out where this is. So if I do it relative to this spot, I can find out how far away in this axis it is. So let me just zoom in a bit on the triangle. I want that distance, which I'm going to call x. So this is 2.5. So x is to 2.5. I guess I could do this as just a ratio and not even break down sine and cosine. X is to 2.5 as 3 is to 5. I'm using the sine of the angle here. So x equals 2.5 times 0.6. And I believe that's 1.5 meters. So x is 1.5. All right, I want this side now. And I'm going to call that, it's not really the y coordinate. So I'm just going to put z in here for a minute. But z is to 2.5 as 4 is to 5. So z is going to be 2.5 times 0.8. So z is 2. So that means that this height is 4 minus 2. We all good with that? So this is 2 meters. Just doing the geometry. All right. I think we've got everything we need to actually do this problem now. So I'm just going to get something cleaner for this. I have a dot here. Center of mass has a mass of 3, and it's 1.5 meters from the edge. I have a dot here. Mass is 4, and it's 2 meters in that direction. And I have a dot here that is 1.5 and 2.0 away. I need to find the center of mass. Alrighty. So I'm going to do the x center of mass first. Starting from here and only looking at the x coordinate of each of those dots. I have 3 dots. So my mass 4 kilogram dot is at 0. My 3 kilogram dot is at 1.5. And my 5 kilogram dot is also at 1.5. This is going to be 4 plus 3 plus 5. Well, the bottom of that is, let's see, 7 at 12. I don't know what the top of that is. I mean, 5 times 1.5 is 7.5. 3 times 1.5, is that 4.5? So it's 12. So it equals 1. Okay. Cool. I had no idea. I like where this is going. All right, let's do the next one. Maybe the next one will have a cool answer too. Let's see, the 3 is at 0 this time, but the 4 is at 2, and the 5 is also at 2, and it still has a mass of 12. No, that's 18 over 12. And that's 1.5? All right, so our center of mass is somewhere like over 1 and up 1.5. So our center of mass is like there. So over 1, up 1.5, so like right there. Maybe the center of mass is. All right. Oops, I didn't record any of that. Oh well. Anybody watching at home, didn't record it at all, but there's the whole problem. We just laid it all out. So, wonk. How was that? Is that okay? Do you want me to do any more? Okay. Be cognizant of finding those two forces. Pretty sure we're going to find that one of the forces from the wall is downwards to keep that thing from sliding up, and then, of course, the other force from the wall is that way. I have a feeling not many people actually saw it all the way through, but it'd be nice to set it up. The ball is thrown with an initial velocity this way. So that's the direction of the initial velocity. Do you want up to be positive or negative in this problem? It makes a big difference if you make that choice in the beginning because you need to be consistent all the way through. I think it's best to make the upwards direction positive for this problem because we have two forces acting downwards. We'll have the weight and drag, and they act in the same direction this time. So our net force equals MA, which means negative mg minus kv equals MA. Now, that's the start of your problem. And from here, you need to create a differential equation that could be used to find a function for the velocity. So that means rewriting this like that. Now, this is the start to getting your answer, but to actually continue on, you're going to need to split your derivative and get something like dv equals let's factor the negative sign out. There's no reason that you can't do that, and kind of makes it nice what has to happen next, which is get anything with v on one side and everything with t on the other, which is going to make this negative dt equals m over mg plus kv dv. Now, we're going to integrate both sides. And this is just following the set of steps. I don't think I veered out of the set of steps yet. All of this is algebra. The only thing that's kind of not algebra is that substitution. But it's really just algebra. And you have to set your limits here. And here's where I'd be very careful. At 0, we have a positive initial velocity. And there's a desire to put 0 in for the final velocity, but don't do that. Put v for the final velocity. We want an expression for v as a function of t. We'll get 0. We'll be able to find 0 out, no trouble. 0 is a condition of the problem. And we just want to find out, we want a function. So we want 0 to t. The left side of this is cake. It's easy. You put in t to the 0 power, do your integral. And this side you'll get negative t. Now this side, definitely harder. Definitely harder. 4, 5, and 6A were actually done in 6th period. I will do them again, not a problem. I am going to start at number 1 though, since some people couldn't make it off number 1. So here we go, A uniform 10-meter long plank of wood of mass 60 kilograms is centered on two cinder blocks that are 6 meters apart. What is the normal force on the cinder blocks from the plank if a person of mass 90 kilograms stands at the center of the plank? Do I have to do that one? A lot of symmetry there. Okie doke. Message received. So, plank, 10 meter long. Here's our 10 meter long plank. And it's on a couple of cinder blocks. Cinder block number 1. Cinder block number 2. And we're told that they are centered, but this is 2 meters, and this is 2 meters, and there are 6 meters between them. Okay? Any question about that? All right. I'm going to get rid of some of those. The plank itself has a mass of 60 kilograms, so there's 600 newtons here, and how big a person? 90. So a 90 kilogram person stands here, so there's another 900 newtons straight down. This problem is perfectly symmetrical. I'm not going to bother to do the torque problem. It's centered. So these two upward forces are going to have to be equal and identical, but they have to sum to give me 1,500 newtons. So problem A, 750, 750, and we'll call it a day there. Okay, so the guy stands 3 meters in from one side. All right. So now we actually have a problem to do. Let's do that one. So 3 meters in from one side puts him right about there. And we're trying to figure out the force on the cinder blocks. So we're going to need both of them. I think it's obvious to me, but maybe not to you, that this one is going to be greater than this one. Does that seem realistic? All right, so I'm going to put NL and NR. We're going to eliminate one of these and then to find the torque. But right now, NL plus NR has to equal 1,500 newtons. That's the net force problem. That's still the same. So I'm going to put the pivot point here. And that eliminates one of our unknowns. So whatever we find for NR, NL has to equal the amount necessary to take the total up to 1,500. Everybody good? All right. I'm going to need this distance. So 5 meters. Is that all right? I'm also going to need this distance, which 3 meters. We good? Okay. So 3 torques are going to balance to be equal to 0. The torque from the 600, the torque from the 90, and the torque from the normal force. Based on right-hand rule, let's see, the 600 is going to be a negative torque, and the 900 is going to be a negative torque, and the torque from the cinder block is going to be a positive torque. And I'm still just using out of the board as positive and into the board as negative. And they have the sum to be equal to 0. Now, once I set this up, this is the same problem for the rest, right? You're just going to change where the guy is. So pay heed that I'm not going to do all the other parts to this problem because it's kind of repetitive. You need to practice, but I don't need to practice. The way this problem is set up, all the angles are 90 degrees. 3 buckets, right? If I start with the weight of the cinder block, of the plank, it's 3 meters in and it's 600 newtons. The person, 5 meters from pivot, 900 newtons. And the other cinder block, I don't have that written there, but that's 6 meters. And it's an unknown force. Any questions? As the sum to be equal to 0. So slide that a little bit to the right. I'm sorry, a little bit to the left. I get 6nr has to equal 1800 plus 4500. Um, 18 and 45 is 63. Pretty sure. And I don't know, 15? No, 1050. Is that right?
Yeah.
Newtons. So NL 450. Is that all right? Any question about that? Yep.
I thought problem 1 was asking the normal force that was weighing down upon the cinder blocks.
Well, I agree. The plank applies a force to the cinder blocks, but the cinder blocks has to apply an equal and opposite force to the plank, so that their balance of forces is equal to 0.
And what about the weight of the cinder blocks? Wouldn't that?
Cinder blocks aren't on the plank. They act on the ground.
I'm sorry.
No. I clearly misconstrued the point of the question. This is the point of the question. This is what I wanted you to find out. So I don't ever mistake. So I still have 600 newtons of force acting at the center of the plank. The guy stands at the end, and I have 900 newtons of force here. The plank is still having to be held in place. I assume there's a normal force on the left and a normal force on the right. But look, it's possible that the system is pivoting in this direction, and this isn't an upward force at all, but you're going to have to hold down on the end of the plank to keep it from, spinning. There's a good chance it probably does that. In fact, that's what the problem is asking. Because that's what the problem is asking, I'm going to put the pivot point here. So I'm interested in that. It's still NL plus NR has to equal 1,500 newtons. That's still true. None of that has changed. But with the pivot point there, I've still got 3 torques. Torque from the normal force, torque from 600, and torque from 900. 3 torques. They still have the sum to be equal to 0. Still 3 things. Largely the same things. Still 90 degrees because it's a horizontal problem. So, as problems go, this is, kind of very similar to what was just done. The normal force from the pivot to here is 6 meters. We don't know the size of that force, and it's attempting to turn that way out of the board. That's positive. Any question about that? Actually, I'm sorry. The way I drew it, it's negative. Sorry, negative. Negative, that way. Yeah, negative. Let's see. The 600 is 1 meter away from the pivot point, and it's out of the board. It's positive. And the 900 is 4 meters away from the pivot point. It's into the board. It's negative. Any questions about any of those choices? Alrighty. Then I get negative 6NL equals 3,600 minus 600. Set them all equal to 0 and got NL on one side by itself. This is 3,000 equals negative 6NL. So normal force on the left is negative 500 newtons, which means I've drawn it in the wrong direction. In order for us not to have this thing slide off, this thing has to pull downwards. It has to pull downwards a lot. But there's something else interesting here. If you carry this on a little further, you find that the normal force from the right-hand cinder block has to be 2,000 newtons. This cinder block has to apply more upward force than the weight placed on top of it. This is because of the leverage of the guy standing on the end. And this is how things like pliers and nutcrackers and all those things work. They gain force at the expense of distance. That's a simple machine. So if you think about a nutcracker, it is this device. Or one of those things you use to, it's something long like this. Hinged here. Place the nut there and you squeeze here. Right? The idea is that you're acquiring leverage. The torque that you get by having the longer torque arm and this force increases the amount of force here because of the shorter torque arm. So nutcracker works. It's a type of lever. In fact, this, which has a hinge here, it's like a class 1 lever or a class 2. I don't know what the classes are. It can acquire more leverage than a pair of pliers can. Because pliers don't have the same amount of mechanical advantage. They have less mechanical advantage. A pair of pliers, see if I can kind of compare a pair of pliers or a pair of scissors. They're hinged here. The mechanical advantage comes from the ratio of these two torque arm lengths. The ratio is less, so you get less mechanical advantage. But the nice thing is the thing that you're trying to grab onto can be in front of you. You don't have to wrap the pliers around them. So, anybody who uses tools knows all about this. So, if you guys don't use tools, well, that's the whole point of them. Gaining a little bit of mechanical advantage. I want you to understand that I don't find this to be valuable unless when we get to the end you understand why you remove the numbers. If all you're going to do is blindly write down what I write down, waste of your time. Okay? Just a waste of your time. So I don't know who asked about it, but here we go. I'm going to skip part of the problem because we did do the entire thing already. And I'm just going to focus on recognizing that the forces are acting on the ladder. I've got the ladder horizontal, and based on the information given, we've got a frictional force this way and a normal force from the ground this way. This is the angle theta as indicated in the problem, making this angle 90 minus theta as indicated in the problem. That's going to be important. Pay attention. There is a force of weight here from the ladder that's also acting at an angle of 90 minus theta. There's also the weight of the person acting at an angle of 90 minus theta, and they're located at a distance d from the end of the ladder. But there's also a normal force from the wall that acts at theta. It's at the end of the ladder. The ladder has a center at L over 2, and the ladder is L long. So that's where everything acts. All good? No feedback? So am I doing this by myself? Any questions? Somebody asked about it. I hope they're paying attention. Moving forward, I still think net force in the x direction equals 0, so friction and normal force from the wall have to be equal. And net force in the y direction also equals 0. So normal force from the ground and has to equal the two weights, right? Yep.
Wouldn't normal wall be 90 degrees?
Nope. Doesn't the ladder make an angle with the wall?
Yeah.
Does that make sense?
A little.
I don't have time for you to find that. The torque is the big part, right? So I chose as a pivot point here, and now is to eliminate two of the unknowns, and I think that works good. That leaves 3 torques acting in the system. We want the system to be balanced, so I'm expecting that those 3 torques will sum to be equal to 0. So there's a torque from the ladder, torque from the person, and torque from the wall. Our 3 torques. Torques have 3 things. Here we're going to have to be a little more careful, I think. All right. Torque from the person acts L over 2 from my pivot point with a force of mg and an angle of sine of 90 minus theta. Sine of 90 minus theta is cosine theta. I'm under the impression you know that. If you don't know that, I can prove it to you, but you need to do your part and play along. So if you don't know that that's true, you should ask about it. But this is a pretty straightforward trig identity, because what is the opposite side for one angle is the adjacent side for the other angle, which is why this works. But draw a triangle. You'll see that it has to work. Yes, sir.
We're using theta instead of phi now.
The problem defined theta. I'm using what the problem said to use. Keep going. Alrighty. I will assume nobody needs to see the triangle stuff then. That's good. Very impressed with your ability to comprehend that right off. Good job. What direction is this? Well, that's into the board, so I'm going to go with negative. Next one, it's also negative, and that's going to be big M times G. Oh, wait, wrong thing. D right here. Then big M times G. And then it's also going to be sine of 90 minus theta, so I'm going to put cosine theta. And last, normal force on the wall acts all the way out at L. It is positive. It is just the normal force on the wall. And it is acting at theta. So there we go. Those are our 3 torques. They have the sum to be equal to 0. Alrighty. Good to go? Okay. Got to add all those together and solve that for the normal force from the wall. The reason? Normal force on the wall is equal to the frictional force. That will give us a way to compare the frictional force on the ground from the normal force on the ground. That's what we want. We wanted coefficient of static friction. We want this. And this is the normal force from the ground. So we are using the normal force from the wall to give us that, and we have the normal force from the ground. We want to compare them. So all of this was about doing a force problem. I'll add these together, and I'm going to get negative L halves mg cosine theta minus d capital Mg cosine theta plus L nw sine theta. We need to solve this for nw. This all equals 0. So I'm going to skip most of the algebra, or at least try to. I'll have mg L over 2 cos theta plus mgd over, nope, just mgd And now divide both sides. Boy, this is kind of hideous. But this is what it is. There. I can do algebra like anybody else can. I'm assuming you guys do algebra, but let me tell you, it was rough in my chemistry class. I'm amazed at what they're incapable and unwilling to do. I'm a little surprised at you guys. Now that I know what you guys are like in Chem Honors, I'm surprised this class exists at all. It's a long way from Chem Honors. Long way. I think it's appropriate to simplify this a little bit because there are some things you can do here and they make some sense. For example, we can fold the L sine theta into this and get mg over 2 cotangent theta plus mg d over L cotangent theta. We could factor the g and the cotangent out. And there's reasons to do that, but I think I'll leave that for this minute. Because this equals friction. And friction has to be less than or equal to mu times the normal force from the ground, which is mg plus mg. We're trying to get an expression for friction. So I've just brought the other pieces together. If you need me to, I'll scroll over there so you can see them. All right. We're going to solve for mu. So mu has to be greater than or equal to mg over 2 cotangent theta plus mg d over L cotangent theta all the way over mg plus mg. Now this can be cleaned up some, and I think it's worth cleaning it up and looking what you get. So I'm going to cancel out what's in every term, which is g. G is in every term. I'm going to factor out cotangent. And what I have left in here is m over 2 plus m times d over L all over m plus m times cotangent theta. Now, you might not see why this has value, but there's a lot in here that has value. If your job is to try and make something, if your job is to build, if you're putting a sticker on the side of this ladder, or you're deciding where the warning signs are, do you see all the things that are, affecting how much friction you better hope you have on site? The truth is, you could solve this for anything. You could solve for theta, you could solve for mu, you could solve for how high up on the ladder you can stand. It's all in this expression. And those are the factors, right? This is a factor. This is a factor. You probably don't have any control over that. Solving for this was just a way to get you guys to put this together. Truth is, I'd probably rather solve for the angle and figure out what things lead to what angles you can use. Having a cotangent here, that's interesting. If you know anything about the way your your trig functions work, cotangent goes to infinity in some directions and 0 in the other. That leads to some interesting predicaments if you're the one standing on the ladder. Please also notice that if you know the trend in cotangent, then you know whether increasing whether increasing theta is going to require an increase in your coefficient or a decrease in your coefficient. But staring right at you is this ratio, D over L. That's a big deal because you got m over 2 on one side. That's going to make sure that this fraction is less than 1. That's good. It needs to be, because you can't have a coefficient of friction that's greater than 1. But you're still dealing with the cotangent, which can clearly be greater than 1. There's plenty of angles where that's true. But boy, this ratio means a lot, doesn't it? It means a lot. It really determines what that coefficient is. You start getting up high on that ladder, you make a difference whether that ladder can hold you or not. Now, they've made assumptions about what the ground's going to be like. But any ladder probably has feet on the bottom that allow you to switch them to something that might have claws in it to grip the ground a little bit better, in case you're in a situation which the ground is a little more slick. Maybe you need your ladder when it's snowing out. I don't have that problem here, but I can imagine it. There's also quite a few slick surfaces around your house. Cement that gets a little bit of stuff on it can become quite slick all of a sudden. So there's a lot here. I think it's this is how they figure that stuff out. How they know where to put the label on there that says don't stand on this step. In your head with all your bravado, well, why is the step there if I can't stand on it? I'll stand where I want. You won't tell me anything. I'm an American. I have no trouble doing number 5. However, when we did this the first time, I suggested that you look on a integral table to be able to do the integral portion of this problem. You guys remember that? There are a few of you who are taking calculus and you've now begun the integral in AB. And all of you who are in BC have done enough work in BC to understand how the chain rule works and therefore how U sub works, which means this problem can be solved using U sub. And so I would be remiss if I didn't at least introduce that a little bit, since you're learning it in your calculus class. Now, all the rest of you, look, we're going to get to something that you don't know how to do. And I'm not expecting you to just learn it overnight or perhaps even learn it at all. You can still open up the integral table and do this problem using the integral table. It's right there in front of you. Get your equation sheet out, look at the integral table, and do exactly what we talked about in class. But I think it's not a terrible idea that we fold in a little bit of stuff that people might be learning outside of this class. So if that's you, maybe before you raise your hand and say, why are you doing that? Let me know if you're in calculus right now or not. Because if you're not, look, just do it the way we talked about in class, or don't do it at all. Skip this and lose the 3 points. Okay? Most of this problem is algebra, though. The ball is thrown upwards into the air. It has an initial velocity, v0. I am making the upwards direction positive, which means the ball is experiencing 2 forces downwards. The weight of the ball and the drag force on the ball. So you're asked to come up with an expression for velocity as a function of time. This is going to require a differential equation. Where do you start? Well, they gave and talked about forces. The best place to start is Newton's second law. There's a built-in derivative in Newton's second law, which is why I've told you to start here. The most likely question will be for you to create a differential equation. Let's create the differential equation. Negative mg minus kv equals m dv dt. There, we have created the differential equation. That doesn't tell us anything yet, but you've done that part. Now, you could go further. So if the next part says, using your differential equation, come up with an expression for v as a function of t, your next step is to start the process of splitting the derivative, which will mean to isolate the derivative first. Step 1, right? Isolate the derivative. Step 2, split the derivative. Still all algebra. Step 3, collect terms. Collect terms means to get anything with t in it on the side with dt and anything with v in it on the side with dv. So still no calculus. And even the next thing we're about to do isn't calculus. All I said was draw the integral symbol and set your limits. That's not calculus yet. I drew my calculus symbol. At time 0, my velocity was positive v0. The bottom, we set the initial conditions. The top, we set the future condition that we're looking for. V is a function of t. All right. That's everything except for the calculus. We still have calculus to do. Yes, ma'am. Okay, so we're going to go on to the next step. But this is the step where some of you are going to have trouble. The left side we've done already, right? So I don't feel so bad in saying that this is just negative t. We've done it enough times. If that's still a problem for you, remember this is t to the 0 power. Add 1 to your exponent, divide by the new exponent. But we've done that a lot of times, so I don't feel like I have to keep doing that. I'm looking around at the people whose faces will probably ask me about this later, so am I good to move on, or do I have to explain it yet again? Okay, so I am moving on. Because it is the other side that's going to be a problem. In order to make the other side a little bit better for you, take the m out. So we need to take and do this integral. This is outside the scope of this class. You can look it up on an integral table, or you can do what's called U substitution. So all of you who are in calculus, this is what U substitution is. We know as calculus students that there exists an integral for 1 over u du that is the natural log of u. We know that exists out there. The point of choices.
It depends what people want. I may or may not put a list together if no one wants to vote for anything.
Oh, I'll
It would
vote.
be like a poll.
I want to read Alas Babylon. I've never read it. Or Lord of the Flies, because I've never read it.
We'll have to stick it to books that everyone can understand, so it has to be freshmen through seniors can understand it. And it has to be that it's short enough to read within a month.
That's true for both of those books.
I've met some interesting freshmen.
Well, I can't read any of those Dick and Jane books anymore. They're not as much fun, but I love Green Eggs and Ham. It's on my bookshelf. All right. Well, I'll take it under consideration, but here's U sub. I'm going to make all of this simpler. I'm going to do so by saying that U equals mg plus kv. Now, to do this correctly, we're going to be taking my integral and subbing in u for that function. The problem is that we have dv here, and this requires that we have du. So we take this function and take the derivative with respect to v. So I get du dv. The derivative of a constant is 0, so the derivative of mg is 0. And the derivative of kv is going to be kv to the 1 minus 1 power times, oh, that's it. We pull the inner things down, times 1. All right, you pull down the exponent, then you subtract 1 from the exponent. That's how you take the derivative of a polynomial. We did that first semester. So that means that du dv equals k. So I need dv by itself. So dv equals 1 over k times du. This is called U substitution. And now that I have an expression for dv, I substitute that in to take the place of dv. And I have times 1 over k du. K is a constant. It goes out front. So I have m over k, the integral of 1 over u du. Now, like I said, U sub is a technique. It is the opposite of the chain rule, basically. So you guys who learned the chain rule in calculus, this is the opposite of it. I have this at the ready. So now I can substitute in my known expression, m over k times the natural log of u. But here's where I have to be careful. I have an expression for u. It was mg plus kv. So this is really going to be and I have to evaluate this based on the limits I had, which was v naught to v. So there's a lot with U sub that you have to be mindful of. It's not for everybody, and I do not expect everybody to learn it, but you can practice. It's something that's worth learning. We have 4 months until the exam. It's the same expression every time. If you looked at this one compared to what we did in class, it's the same expression. There's only 2 or 3 of these. This still all equals negative t. That hasn't gone away. I do have to put in my limits, so I'm just going to say this is negative k over m times t on that side. Just moving this over. And I'm back to just doing algebra now. Put in my first limit, subtract my bottom limit. All right, you have to put in the top limit and then subtract putting in the bottom limit. That's what I've done. I have to now solve this for v. This is where the fun begins. It's just algebra, though. Everybody thinks this is all about calculus. It's not the calculus that kills you. It's all the algebra. So, all right, algebra. And I am clearly writing out every step because, I love calculus. It's, just the best. When I am subtracting 2 logarithms, I can divide them and combine them. Why? So I can raise both sides to a base e and get rid of the logarithm. Still not done, but I'm getting closer. Remember, I'm trying to get v by itself, so I think I'll multiply both sides by the denominator. So fun. Maybe not. But I can solve this for mg. I can solve this for v now, can't I? So let's see, I'm going to have all of this. Yay! You still have to divide by k. There's nothing here that looks nice. There is a different way to kind of pull this together to make it look a little different. And you'll need to do that if you want to do the rest of this problem. But at this point, you just really have to divide both sides by k. Now, this expression covers the trip up and the trip down. I don't know if you see that, but it does. It doesn't just cover the trip up. I'm saying that because E for a very long time, this whole thing will become 0. E for a very long time. And so we get as our final expression the same thing we got before, which was the expression for the terminal velocity. And it's negative, indicating it comes back down. So I'd say that's a lot, though, isn't it? Kind of an interesting function. But all right, that was fun.